Hello and welcome to the Energy Resilience Lab. Our lab is dedicated to giving you the knowledge, skills, and the encouragement that you need to become energy independent and energy resilient. Today I wanted to jump in on how we went through kind of options for building your own batteries. So I thought it'd be good to go through the concerns with the cells themselves. So there's some kind of questions floating around with lithium iron phosphate cells if you need to compress them. So that's one thing that we'll go over. In addition, we'll go over the limits on the batteries, where you need to stop charging and stop discharging cells to keep them safe and to get the most life out of your batteries. So to get started, we'll start with the compression. So there's different data sheets that you can get for individual cells if you're wanting to build your own battery pack, and from each supplier, and the supplier gets to name all of the requirements in the testing phase so that you can reproduce the results that they're producing with their cells. And so a couple different brands, one in China is EVE, and I believe they were the first ones to release a data sheet that recommended, or I guess commanded, that you use compression if you want to get the cycle life that they have indicated that you'll be able to get. So looking at cycle life with batteries, with a lead acid battery, you're usually going to get between 250 and 500 cycles, which is usually, for an RV application, it would be a couple of years. If you're if they are sealed lead acid batteries, they will last longer. So you can get some manufacturers are indicating 1,000 cycles, and then so you're going to get several years out of these batteries. 3 to 5 is what I've heard and seen in the solar industry with people operating those. Then when you get into lithium, there's NCA and NMC. So Tesla has made NCA famous because they're trying to get to the highest energy density batteries to maximize the distance, like the lifetime distance or lifetime energy that the battery can produce across its whole cycle life. So they've made that kind of famous. And with the NMCs, usually they're cylindrical cells, which provide their own compression because they're in a pressure vessel that's cylindrical. So they can engineer it so that as the battery cycles, the pressure in the cell will go up, and that will compress the anode and cathode material together, reducing the internal resistance. So those usually don't require it. It's usually the large format prismatic lithium iron phosphate cells that need compression. So if you don't compress it, you're likely going to be fine. So you're still going to get thousands of cycles on that battery. And in most cases, like if you're using it in RV or home use for resilience, you don't need that many cycles. So it's fine. You don't have to compress it. But if you are trying to get the most resilience and most use, and you're trying to become energy independent, where you're actually charging the battery, keeping the energy on site in your battery and then utilizing it on site, then that's where it gets more critical, because you're going to want to use as much as the battery as possible to claim that ROI over time. So on here, I'll tell you, you should do compression on the cells, and it doesn't have to be significant compression, but you at least have to hold the cells precisely. So if you strap them with plastic or steel straps with sufficient support material at the ends so that you're not damaging the batteries with the strain there on it, then that is enough to start well and then have the longevity that you need. What you're looking at is kind of a 3x increase on cycle life. So if you're running a cell and it's uncompressed, you are going to get maybe 1,000 cycles, where the compressed cells will last for 3,000 cycles. So And the main contributor to the failure is that they become more and more resistive. So the internal resistance is very slight. In the large cells, like a 280 amp hour cell, you're going to be at 0.1 milliohms of internal resistance. But originally, from the battery manufacturers, they said that they would say that if the internal resistance doubles, then that cell is ready for recycling. Now, with all the competitive nature in the market, suppliers are saying you can get 3,000 cycles, you can get 10,000 cycles, you can get 12,000 cycles. And now they're just pushing out that internal resistance. So they're saying, okay, now recycle it when it's 4x the internal resistance that it originally had. So it's kind of a gimmick. If you look at cells when they're operating, they do have, the internal resistance does matter. And as it doubles, your control systems have to be able to manage that. So if there is a deep draw on a cell and you've got 4x the internal resistance, you need to have a Kalman filter or some other noise filter and plant model for that system to be able to guess what the internal cell voltage is of the battery. So if you're at 2.5 volts and you have a hard draw and your measurement goes to 1.5 volts, that would be an absolute minimum, and the BMS should turn off anytime it gets below 1.5 volts. But that is a steady state 1.5 volts. And so if you're drawing at 100 amps, it might be an artificial low, and you're going to get some nuisance trips of the BMS because you don't know what the actual cell voltage is. So first thing, compression, do it, no reason not to. Second thing is the reason for a BMS on lithium batteries, we'll just focus on lithium, is to balance the cells. So when you have a battery pack, you need to ensure that there's no parallel draws on any of the cells. So the BMS connects to every point in the battery, and all of your loads need to connect from the top and bottom of your battery, because the current through a series circuit is always the same. So you have to ensure that that's the case. If you do draw on one of the cells independently, it's going to drain that cell, and the BMS isn't going to be able to draw enough from the other cells to keep it balanced. And so you should always isolate any loads from individual cells and only have loads across the whole battery bank. So once you know that, BMS is there to protect. So it's watching all the cell voltages, and we'll stick with lithium iron phosphate because I'm the most familiar with that. But the top voltage for lithium iron phosphate is 3.65 volts, and if you're off by 1/10 of a volt for more than 12 hours or so, the battery will swell, the internal resistance will go out of control, and you've actually destroyed the composition of that battery, and it needs to be recycled. And so the BMS, what it needs to do is it needs to be balancing the cells and controlling the current in and out of the battery. So when you're charging, you want to go up, and you can go slightly past. Usually BMSs will go to 3.75 volts because that just gives it a little bit of headspace. So it can charge to 3.5 and then at 3.75, and then the BMS will lock the current coming into the battery from coming in, and it will use the internal circuits to balance that cell back to 3.65. And so what you're doing is every time you hit those end points, it's giving the BMS time to correct that cell and get it back in sync with the other cells. So that's the top side. At the bottom side, usually with lithium iron phosphate, you should look at the data sheet of your battery, but the cutoff voltage for that cell will usually be 2.5 volts. You can go to 2 volts. It only gives you a few percent more capacity, and it is causing a larger decay on that battery, on those batteries. And so as As far as I've heard, working with these batteries for years, going down that low is fine. You can do it. I know that the Chevy Volt was very rigorous on this. They would try to get every bit of energy out of that battery, because in their case, you don't want to carry around dead weight, and so you want to utilize all the energy possible. And so you want to charge it as full as possible, discharge it as deep as possible, and get the maximum. So that's the bottom side. So just look at the data sheet. It'll tell you where it needs to cut off. And then if you ever do find a battery that you've left out for a long time and it is below 1.5 volts lithium iron phosphate, that battery needs to be recycled. So if you're going over voltage or under voltage, it actually breaks down the composition of the cathode material, and it makes it dangerous to charge. So it's going to cause either high resistance, so that's going to cause the cell to heat up, or it's going to cause an actual breakdown where the composition has failed and the different molecules have cracked and become volatile, or at least not in a safe condition to charge. So those are the limits, top and bottom. So you need current protection, you need voltage balancing at least, and that's where it's going to draw a little current to get it back down to the voltage that's safe for it to just rest. Another concern when you are building your battery is that you need that overcurrent protection to be able to handle the amps that are going to be commonly drawn from your system. So you need to size your BMS, make sure it has the overvoltage, undervoltage protection where it's going to lock out the MOSFETs or relay that's protecting it. And then that relay or MOSFET sizing is critical, because you need to be able to pass enough current to supply the loads. So if you've got a 2000 watt inverter, you need about 150 amps at 12 volts. And so you need to size that properly. If you get on the market, you'll be able to find different batteries that can handle a certain number of amps. And you just need to make sure it can handle enough. You can augment the system by putting batteries in parallel. So if you have two batteries that are rated at 100 amp discharge and your inverter needs 150, you could size that system by putting two batteries to supply the current. Because when the current is drawn from two batteries, as long as you made symmetric wiring to the batteries, the current will divide, and half the amps will come from one and half from the other. So you're going to have a 75 amps coming out of each, and that's totally fine for a 100 amp battery. So thank you guys for tuning in. This is critical if you're going to make your own batteries, and I just want to make sure you guys understand what the ins and outs are for the BMS, so that you're not building batteries that they all cost money, and as they fail, or if they fail because you don't understand, and that's a very bad condition. So feel free to reach out if you guys have any questions, and we'll be back next week with more tips and tricks. This is for building your own batteries from scratch with cells and packaging materials and your BMS of your choice. The main benefit of doing it this way would be to be able to size the current capability of your battery to match your system. So you can make a 100 amp hour battery that can discharge at 300 amps or something for a short amount of time, because that's what the cell can do, where manufacturers don't usually do that. So thank you guys. Keep up the good work, and keep me posted on any of your projects or questions. And I just want to say, go team. You guys get out there, get up off the couch, get out, get in the sun, think about your life, see where you can become more resilient, and we'll all be better for it. Go team. Have a great day. We'll talk to you next week. See ya.